In this videotape, we'll take a look at motors in general and motor protection in particular. Working as we do in the electric power system, we tend to forget the vital role that electric motors play in everyday life. Motors come in a vast range of sizes, from tiny battery-operated fractional horsepower motors to large motors, 10,000 horsepower and up, driving heavy machinery. Similarly, the level of voltage used to feed motors ranges from 120 volts for domestic equipment up to, say, 15,000 volts for large industrial machinery. Most industrial motors provide terminal blocks which allow the user to connect the stator windings in Y or delta according to voltage requirements. In most industries, motors form the backbone of the whole installation, driving conveyor belts, pumps, compressors, machine tools, and the like. In the electric power industry, motors have widespread application, particularly in power stations, where they drive boiler feed pumps, boiler fans, and a multitude of other equipment. In the substation, motors will drive transformer fans, oil pumps, disconnect switches, and so on. Because of this wide application of motors throughout the power system and also across the whole range of our customers, we need to know the characteristics of electric motors, typical faults which may occur, and the protective devices which are installed. We are particularly interested mainly in the larger motors whose performance may reflect back into the power system. The electric motor is often forgotten in our day-to-day work, so we feel that it will be worthwhile first to review the main characteristics of both induction motors and synchronous motors. We'll be looking at synchronous motors later in this tape. For now, let's concentrate on the induction motors. The operating principle is very simple. The stator windings are placed around the stator iron core in such a manner that when a three-phase voltage is applied, a rotating magnetic field is set up around the rotor. Usually, the rotor is nothing more than a series of solid conductor bars short-circuited at each end to form what looks like a squirrel cage. You know the type when the squirrel or mouse runs to spin the cage. In order to improve the magnetic circuit, the conductors are embedded in a laminated iron core. The flux of the rotating magnetic field cuts the rotor conductors and induces a current flow as the conductors are short-circuited. Interaction of this current with the flux produces a torque which causes the rotor to rotate. At what speed does the rotor turn? Well, we know that the magnetic field is rotating at synchronous speed. On a four-pole machine, this would be 30 revolutions per second or 1,800 revs per minute. But the rotor can never attain that speed. Why is this? Well, if the speed of the rotating field and the rotor were identical, there would be no current induced in the stator conductors because there would be no relative movement. Consequently, the flux would not cut the conductors. In this situation, the torque developed by the rotor would be zero, with the result that its speed would fall back. The actual difference between operating speed and synchronous speed is known as slip. Typically, the value of slip will vary between 1 and 3% as the load increases from no load to full load. Let's look at the startup curve for a motor which is driving a large boiler fan. Plotted along the bottom, we indicate speed in terms of percent synchronous speed. Here on the vertical axis, we have stator current. When the stator winding is first energized, the rotor is stationary, so a very large stator current is induced into the rotor conductors as the rate of cutting by the rotating flux is maximum. Correspondingly, a very large stator current is drawn, perhaps 7 times full load current. As soon as the rotor begins to accelerate, the current drops rapidly to about 5 times full load current and remains fairly constant at this level until the speed reaches about 80% of synchronous speed. At this point, as the rotor approaches synchronous speed and the slip rate reduces, the stator current falls off rapidly until at 100% synchronous speed it is zero. As we just mentioned, the induction motor cannot operate at this point. Now, keeping this curve in mind, let's change the vertical axis to indicate the torque developed by the rotor as it runs up to speed. Torque refers to the amount of mechanical turning force which is available to drive the fan. The torque required by the fan is indicated by this line, which is almost a straight line from zero up to operating speed. When the motor is first switched on, this small amount of excess torque is available, causing the rotor to accelerate. At about 40% speed, the torque developed by the motor increases, and so consequently does the acceleration of the rotor, until about 90%. This point is known as the pull-out torque. From this point, as the speed approaches synchronous speed, the amount of torque available rapidly falls until it is zero at synchronous speed. As we know, this is because the magnitude of current induced in the rotor conductors decreases as it approaches synchronous speed. The motor will actually operate at this point here, where the torque developed by the motor equals the torque required by the fan. Now let's see what happens when the fan load is increased. For example, suppose we doubled the torque requirement. In this case, the speed would drop back by a few percent, and the stator current would increase. It would probably double. But look at this point here. Any increase in the torque requirement beyond this maximum point would result in the motor stalling, because the torque available is less than that demanded. This is why this point is known as pull-out torque. The actual speed at which pull-out torque occurs is determined by the design of the motor. In fact, it depends upon the ratio of the resistance to the reactance of the rotor conductors. In this example shown, the R over X ratio is 0.1. That is, the resistance is 1/10 of the reactance. This curve shows the motor characteristic where the resistance is 1/2 the value of reactance. Note that the characteristic of the motor can be changed to meet the requirements of certain loads by adding or subtracting resistance in the rotor winding. But how can we do this? Well, this is achieved by using a wound rotor instead of the squirrel cage. The rotor winding is no longer short-circuited. Instead, it's brought out to slip rings, and these in turn are attached to an external resistance which can be varied to suit the requirements. Obviously, another effect of this is to provide variable speed control. Now, let's look at the various types of faults that can occur on a motor. The first that comes to mind is insulation failure on the stator windings. The consequence is a phase-to-ground fault, as the insulated conductors are fitted tightly into the slots of the iron core. In many cases, this fault also leads to a phase-to-phase short circuit in addition to the ground. We'll be looking at protection schemes for fault conditions soon. A more common problem of the motor is overheating, which may go unnoticed over a period of time. Overheating leads to deterioration and eventual failure of the insulation. This causes a short circuit between phases and to ground. Overheating may be caused by a variety of reasons. The obvious condition that comes to mind is that of overload, where the driven machine, say a fan or pump, is working above the motor's rated capacity. As we have already learned, this leads to considerable increase in current flow through the stator, which causes overheating if the condition is allowed to persist. If the overload is very great, perhaps due to a mechanical defect, then the motor will stall. This is known as the locked rotor condition. The stator current increases to a high value, perhaps 7 times normal rated current. This condition can cause severe damage to the rotor and stator windings within a very short period of time because there is no cooling with a stationary rotor. Another cause of overheating is low voltage. Even when the driven load is normal, excess current will be drawn by the stator windings. Overheating will also be caused by the loss of one phase of the supply voltage. For example, if a single fuse failed, the remaining two phases would draw excessive current to continue driving the load. Even a difference between the three-phase voltages of the power supply will cause overheating. As you know, these unbalanced system conditions will cause negative sequence currents to circulate in the stator windings. These negative sequence currents set up a magnetic field rotating in the opposite direction, and this produces considerable overheating of the iron core. For example, a voltage unbalance of, say, 3.5% may produce a temperature rise as high as 25%. We mentioned the problem of undervoltage. An even more hazardous condition can occur with complete loss of voltage, particularly on large, heavy machines. If the voltage is restored quickly while the machine is still running down in speed, an extremely large current will be drawn by the motor as it attempts to arrest the fall in speed and then accelerate the machine up to normal speed again. In some cases, this acceleration has even caused the drive shaft to break due to the inertia of the heavy machine. Summarizing then, the faults which we must protect against are insulation failure leading to phase and ground faults, overload leading to overheating, stalling, that is, locked rotor condition, unbalanced power supply, undervoltage, loss of voltage, and rapid restart at reduced speed. Now, at this point, before we start to look at protection devices, let's take a break. Please switch off the tape and review this material in your workbook. The type of protection installed depends very much upon the size of the motor and its operating voltage. Generally speaking, motors up to about 1,000 horsepower operate at 600 volts or less, while larger motors commonly operate at 4,000 volts or higher. Small motors are generally energized through a contactor switch, which provides some built-in protection. The contactor is held closed by the contactor coil. If the supply voltage falls below, say, 60%, then the contactor will open and remain open until the operator effects a manual start. So this provides some protection for loss of voltage. Also, a thermal overcurrent relay is usually built in to protect the motor against overcurrents. Heavy overcurrent heats a bimetallic strip which opens and interrupts the power supply to the contactor coil. This arrangement is not very precise, and for medium-sized motors, say 300 horsepower and up, the contactor switch is operated by external protection relays. Typically, the starting circuit looks like this. The motor is supplied from the 600-volt bus through fused disconnect switches. The contactor control circuit is energized through a small transformer to reduce the voltage down to about 120 volts. In order to close the contactor contacts and start the motor, this contactor coil must be energized by simply closing the push button. This will close the seal-in circuit, and the push button can now be released. As long as there is voltage on the contactor coil, the contactor remains closed and the motor will run. To stop the motor, we must press the stop button to open the circuit. Protective relays operate in the same manner, that is, by opening their contacts in the contactor coil circuit. So let's now add the protection devices. First, overload protection. CTs in the supply leads measure stator current with the secondary feeding a thermal relay, number 49. The thermal relay provides overcurrent protection. It consists of a heater element which operates a bimetallic switch. Excessive current flow will cause the switch to open and so interrupt the power supply to the contactor coil. Now, although we definitely want this relay to trip to prevent overheating of the motor, we certainly do not want it to trip for low-level, permissible overloads. So the relay must be chosen and set to match the thermal limit curve of the motor. For example, this curve provided by the manufacturer shows the allowable time for specific values of overcurrent for a particular motor. This shows that the motor is allowed to carry twice rated current for a period of 1,000 seconds, say 16 minutes. But it is only permitted to carry 6 times rated current for a period of 15 seconds. The thermal limit curve is actually a composite of several undesirable conditions. The upper portion shows limits of overload when the motor is in operation. The lower limit shows the locked rotor condition, that is, the magnitude of current and its allowable time limit. The center portion of the curve shows the current limits that are recommended while the motor is running up to speed. We can also show on this same diagram the curve that represents the stator current during startup. As you will remember, starting current is about 9 times normal rated, but within a few milliseconds, this falls to just under 6 times. This is approximately the same value as the locked rotor value, as you would expect. After about 12 seconds, the current falls to normal rated value as the motor achieves normal operating speed. Now, if the thermal relay was set to trip, say, in this area, we would not be able to start the motor. With just under 6 times rated current, the relay would trip in less than 2 seconds. So the thermal relay curve has to be set within this area here, between the thermal limit curve and the startup curve. In practice, we try to adjust the relay so that its tripping curve is quite close to the heating curve, like this, so as to prevent inadvertent tripping. However, it is quite impossible to get the curves to match exactly, and we will probably find that for high values of current, the bimetallic switch is too slow. For example, at this point, we show the current which the motor pulls when the rotor is stalled. This is the locked rotor position. We can see that if the motor failed to start, perhaps due to a mechanical problem, then the relay would trip some 20 to 30 seconds after the design limit was reached. This could result in serious damage to the rotor. This condition would be aggravated if we tried to start the motor soon after it had been shut down. In this case, the bimetallic switch would cool quite fast, while the motor would still contain considerable heat. In other words, overheating of the motor would take place before the bimetallic switch operated again. One way around this problem is to add a time over current relay. Typically, the characteristic for this type of relay looks like this. We can see that it really trips too early in this region, so it is actually overprotecting the motor with consequent nuisance trips. However, we can combine this with a bimetallic relay by setting the time over current relay for a higher pickup. Now we have the bimetallic relay protecting for the lower values of overload, while the overcurrent relay picks up at about 125% of full load and so protects for the higher values. Another method commonly used is to install a time over current relay only, but have it simply operate an alarm at the lower overload values. However, this method can only be applied where the motors run in a location where operators are in attendance. Both the time over current relay and the bimetal thermal relay protect the motor against overheating by actually measuring current. This has the disadvantage that they do not allow for changes in ambient temperature, which is quite an important factor in determining the thermal limit of a motor. When the ambient temperature around a motor is cold, it can carry overloads for a longer period of time. Hence, the overload protection will probably overprotect the motor and perhaps cause tripping unnecessarily. An improved method of protection against overheating directly measures the actual temperature of the winding and stator core. This method is used in motors above 500 horsepower and must be specified when the motor is purchased. When the motor is constructed, resistance temperature detectors, RTDs, are embedded in the stator slots along with the stator winding. These RTDs, also known as search coils, are connected to a temperature relay which measures the resistance of the detector. As we know, the resistance of any conductor increases as temperature increases. The detector is made of material which has a linear change in resistance as temperature changes. So by measuring the value of resistance, the relay can accurately determine the temperature inside the motor. When the temperature exceeds a specified limit, the relay operates and de-energizes the motor. This schematic shows how it works. The resistance detector forms part of a bridge circuit where the other three resistances are of known value. The bridge is supplied with current from a rectifier. When all of the resistances are of equal value, there is no current flow through the temperature relay, number 49. However, as the motor temperature rises and the resistance of the detector increases, the balance of the bridge will be upset and current will flow through the relay and cause it to operate at a predetermined set point. In the contactor circuit, which we have been studying, this would open these contacts and so de-energize the contactor coil. We know that overload causes overheating, but overheating can also be caused by phase unbalance. Protection is often provided against unbalance by the installation of a negative sequence over voltage relay 47. This is connected to the bus to measure the power supply conditions. The relay is connected to measure negative sequence voltage only. This is normally 0 or at least very low under balanced conditions. The relay is set to operate at quite low voltage when negative sequence voltage rises to, say, 4% of normal terminal voltage. When the relay operates, it trips all of the motors on the bus. This relay also protects against phase reversal of the power supply, which could occur, for example, if a lead on the supply transformer had been reversed during a maintenance period. The relay prevents any of the contactors from closing. This is extremely important because damage may occur to some mechanical equipment if it were made to rotate backwards. Okay, so we have looked at protection against overheating and overcurrent. But what protection is provided in this scheme against a high-level stator fault, say 20 times rated current? For this high value of fault, both the time over current relay and the thermal relay are far too slow, as they take over 10 seconds to operate. Moreover, in many instances, the contactor does not have sufficient interrupting capacity for high fault current. The motor will be protected against this condition by a set of fuses which are located upstream of the contactor. Typically, if the rated current of the motor is, say, 120 amps, the rating of the fuse would be selected to be 200 amps. This line shows the fuse characteristics. It operates before the motor damage curve is reached. We can see that for this high level of fault, the fuse will operate within about 0.1 of a second. The fuse will operate for any high-level fault within this area, below the operating curve for the overload relays. At this point, let's take a break, and then we'll come back and look at protection devices which are used on large motors. For now, switch off the tape and thoroughly review this material in your workbook. In older installations, you may come across large motors operating at 480 or 600 volts. Usually these have special starting arrangements in order to keep down the exceedingly high level of current during startup, and so minimize the size of conductors required in the power supply circuit. One method uses the Y-delta switch. This actually connects the motor windings in Y during the initial startup period, so decreasing the voltage across each phase, and this in turn brings about a reduction in starting current. When the motor is up to speed, the switch automatically transfers the windings to the delta connection and so provides full voltage across each phase. In another method, a tapped auto transformer is used. During startup, the taps are adjusted to reduce the voltage across all three phases. As the motor runs up to speed, the taps are automatically raised to the normal operating position. Nowadays, large motors above 1,000 horsepower are usually supplied from a high-voltage bus, say 4 kV and upwards. The motor is normally switched directly onto the bus through a circuit breaker. A typical control circuit for the breaker is shown here, as discussed in earlier tapes. The breaker closes when the closing coil is energized by this push button. Once the breaker is closed, the control circuit is de-energized by this breaker auxiliary contact. In order to trip the breaker, the trip coil must be energized, and this can be achieved by pressing the manual trip button. In addition to this, several protection relays are connected to close contacts in this tripping circuit, and so trip the breaker and stop the motor. Let's look at typical protection relays which would be installed on a 5,000 horsepower motor operating at 4.16 kV. Some of these items are similar to those we discussed in the last segment, but there are several additional relays. As before, we see that overload protection is provided by a thermal overload relay, and for this size motor, this is invariably of the RTD type. When this relay operates, it will close contacts in the tripping circuit of the breaker, and so stop the motor. In addition to this, overcurrent relays are fed from CTs in each phase of the power supply to the motor. These instantaneous overcurrent relays, 50, are installed one per phase to protect against very high-level stator faults. This relay is usually set at about 1.8 times locked rotor current. Relay 51 here is a time overcurrent relay set to protect the motor against overheating due to overload. This relay should also protect against locked rotor conditions. As before, we have a negative sequence relay connected to the supply bus. In the case of unbalanced system conditions, this would trip all of the motors on that bus. One problem with this arrangement is that it cannot detect an open circuit inside the motor itself, or the circuit breaker, or the supply leads. For this reason, on large motors, an additional relay is often fitted to measure current unbalance. This is fed from the same CTs as the overcurrent relay. The phase balance relay, 46, consists of an induction disc which compares the magnitudes of the phase currents. When the motor is running at close to full load, the phase balance relay will operate if the unbalance reaches 15% or more. Where circuit breakers provide direct on-line starting, undervoltage protection must be installed. This is because the circuit breaker will not open on loss of bus voltage. An undervoltage relay, 27, is connected to the bus. On loss of voltage, this will trip all the motor breakers on the bus, so preventing rapid reclosure while the units are running down. As we mentioned earlier, insulation failure usually leads to a stator ground fault. The best way to detect this is through the use of a toroidal CT, which is connected to an instantaneous relay. All three supply leads to the motor pass through the window of the transformer. As long as the three currents are balanced, the value of CT secondary current is close to zero. However, if a ground fault occurs on the stator winding, there will be significant out of balance, and sufficient residual current will flow in the CT secondary to operate the 50G relay. We have seen this type of ground protection quite often before in this program. It is very sensitive and may be set as low as 10% of rated current. Where the cables are very large and cannot pass through the CT window, then separate CTs will have to be installed and connected to the relay. But this arrangement does have a disadvantage. During the startup period, the current is extremely high, and with transients, the separate CTs may suffer unequal saturation. Consequently, the secondary current will be unbalanced, and the relay will operate incorrectly, and so prevent the motor from starting up. With this type of arrangement, the instantaneous relay will have a high setting, and it will be used in conjunction with a time over current relay 51N, and this must be set to ride through the startup period. Usually, several large motors are fed from the same bus. So in the case of a stator winding ground fault or short circuit, there is a large MVA capacity available. In this situation, the fault current is usually very high, and the instantaneous overcurrent relay is sensitive enough to detect this. However, in some cases, a very large motor is fed by only a single transformer of a similar capacity. In this situation, the magnitude of fault current may be limited. For this type of installation, the best way to detect a stator fault is to install differential protection. Ideally, separate CTs should be provided like this, with a separate relay for each phase. Normally, the differential relays installed are of the restraint type. Preferably, one set of CTs should be placed on the outboard side of the breaker so as to protect against faults in the breaker and supply leads, as well as the motor. The other end of each phase winding must be available, or CTs will have to be built in the motor. Normally, this type of protection is only used in the larger motors, say above 5,000 horsepower. In smaller motors, where both ends of the windings are available, a simple form of differential protection can be provided by using 3 toroidal CTs like this. Both ends of each phase winding pass through the window, and any out of balance energizes the instantaneous overcurrent relay. On large motors, additional protection is usually provided against a locked rotor. If the motor stalls or if it fails to start, excessive current will flow in the rotor windings and cause extensive damage within a short period of time. The value of stator current under these conditions is similar to the startup current, about 5 times normal rated current. From our earlier curve, we see that the motor takes about 10 seconds to start. However, if the motor fails to start, this high value of current would remain on for a longer period. The allowable period of time is shown by the bottom end of the thermal limit curve, In this case, 50 seconds. The instantaneous overcurrent relay is set too high to provide protection. In some installations, the high dropout or instantaneous relay, number 50, is set to pick up below the locked rotor current, but it is supervised by a timer which is set to block operation during the normal starting period. If the high current remains on after the timer has timed out, the relay will trip. Protection against this condition should also be provided by the time overcurrent relay if it is set properly. But this is not so easy as it appears. Remember, the induction relay will pick up as soon as the motor is energized and high locked rotor current flows. Even though the current level falls off, the relay may still time out and trip, usually around this point. The solution is to allow more tolerance by slowing down the relay. It may also trip if the motor takes longer than usual to start up. For example, this could occur if the supply voltage is low. Indeed, switching in a large motor may well cause the supply voltage to dip in certain installations. Under these circumstances, shown by this curve, the motor would take longer to start, perhaps 18 to 20 seconds. But as a compensation, the startup current and locked rotor current are lower. Obviously, considerable care must be taken in setting these relays so as to avoid inadvertent tripping during startup, but at the same time provide adequate protection against motor damage. On some large motor installations, an additional relay is installed to protect against locked rotor. This is the impedance relay. It is set up to measure voltage and current entering the motor, and so measure the impedance. Let's look at this on a resistance-reactance diagram. At start, the impedance of the motor is quite low and consists mainly of reactance, as shown at this point. As the motor runs up to speed, the impedance increases, and at the same time, the phase angle reduces until at normal speed it would be about here. The impedance relay is set to trip for any impedance falling within this circle. This includes the startup impedance. So, how can we get the motor to start at all? Well, a permissive, normally open contact operated by a timer is connected into the trip circuit. This contact will only close after the specified number of seconds for normal startup. Actually, the timer is operated by AC current, so that its operating time will slow down if there is a reduction in bus voltage with consequent longer startup times. When the permissive contact closes, the impedance relay is now able to operate normally and trip for low impedance due to a fault. Yet another form of protection against long startup time on very large motors is provided by an acceleration switch. During startup, this relay measures the speed against time, that is, acceleration. If the startup does not follow a specified curve, the acceleration relay, 18, will operate and trip the breaker. Now at this point, let's take a short break, and then we'll come back and look at protection for synchronous motors. For now, please switch off the tape and review this material thoroughly in your workbook. The main feature of the synchronous motor is that the rotor winding must be provided with a DC current in order to set up its own magnetic field. This is, of course, similar to a generator. The rotating magnetic field produced by the stator locks together with the rotor field and causes it to rotate at precise synchronous speed. As load increases, the stator will draw more current from the power supply system to enable the rotor to continue to rotate at synchronous speed. The DC supply for the rotor may be produced by a DC generator, which is coupled to the motor, or perhaps the supply may be from an outside DC source. Synchronous motors are used where precise, constant speed is required. For example, in synchronous clocks or certain industrial processes. Of course, the system frequency must be held constant, but that's another story. Another advantage of the synchronous motor is that any adjustment of the DC excitation current adjusts the power factor demand of the motor. This is different from the induction motor, where the power factor, about 0.85 at full load, is fixed by design. Reducing the field currents of the synchronous motor increases demand for VARs from the system. On the other side of the coin, and this is its most useful feature, increasing the field current actually delivers VARs to the power system, so the motor operates at leading power factor. This feature is most useful in large industrial installations where the synchronous motor is commonly employed for power factor correction to keep down the cost of electricity. Generally speaking, protection for the synchronous motor is similar to that for the induction motor, but with the addition of a few special relays. One particular condition to protect against is that of overexcitation of the rotor. Conceivably, automatic power factor control or voltage control could result in excessive DC current flowing through the rotor field windings and so lead to overheating of the rotor. Protection is provided by either a time overcurrent relay or a thermal bimetallic relay connected into the field winding circuit. Another, more direct method measures the resistance of the field winding and from this calculates the temperature. These relays are wired to sound an alarm or perhaps in an unattended station to trip the unit. Overheating of the stator winding is protected by overcurrent relays, thermal relays, and current balance relays, just the same as the large induction motor. Another relay often found on synchronous motors is the loss of excitation relay, 40. If field current is interrupted for some reason or another, the motor will operate as an induction motor at lower speed, drawing a heavy reactive load from the power system. This will cause serious overheating of both the rotor and the stator windings. The loss of excitation relay operates by measuring current in the excitation circuit or by measuring the flow of VARs into the stator windings. A power factor relay, 55, is often used, set to operate when power factor falls below about 0.5 lagging. Alternatively, an impedance relay may be used as described in our earlier discussion on generator protection. The loss of excitation relay may be connected to only alarm the operator so that he may restore excitation. Alternatively, in an unattended station, it will trip the unit. In special cases, the synchronous motor is protected against loss of synchronism. This would occur, of course, in the case of loss of excitation. But the motor may fall out of step for other reasons. For example, suppose the excitation was running at minimum setting to correct power factor, and the mechanical load increased above normal. The same could happen if there is a sudden reduction in supply voltage. When pole slipping does occur, the stator current increases, and the lagging power factor falls to a very low value, about 0.25. If the motor continues to slip, the stator current and power factor will fluctuate over a wide range as the rotor tries to pull into step. The out-of-step relay, 78, detects the initial decrease in power factor and trips out the motor during the first slip cycle. One type of design does this by comparing the current in one phase against the voltage across the other two phases. For example, here we are measuring the current in line A by this CT, which feeds into the current coil of the relay. The voltage coil is connected across phases B and C. The phasor diagram looks like this. Here we have the line to neutral voltage VAN, VBN, and VCN. And here are the line voltages VAB, VBC, and VCA. The voltage coil is energized in this direction, VCB, and this is arranged to hold open the tripping contacts. At normal operation, the current IA lags VAN by about 10 to 15 degrees, and therefore has insignificant influence on VCB. However, when the machine falls out of step, IA will increase and also will fall back in phase, so opposing VCB. The relay is set to operate when IA falls below about 0.4 lagging power factor. As you would expect, synchronous motors are fitted with undervoltage relays so as to prevent rapid restart if loss of voltage occurs. This is the same as in induction motors. Additional protection for this condition is sometimes provided by an underpower relay 37. This relay measures power being fed into the synchronous motor, and it is usually set to operate when power falls below 3% of normal maximum operation. That is, close to zero. This relay does have the disadvantage that it could trip if the driving machine suffered surges in power demand, such as in a steel rolling mill, for example. In this case, a reverse power relay 32 would probably be installed. But this relay will only operate if the motor actually feeds power back into the bus. It can only do this if the bus is connected to other motors which can draw the power. In all probability, this would be the case, as most synchronous motors are used in large industrial installations. You will remember in an earlier tape that we discussed special protection required for the generator during startup. Startup protection for the synchronous motor is similar. It's usually provided by the motor manufacturer and includes protection for starting, switching in the field, and synchronizing. Okay, so much for synchronous motors. Now, at this point, let's briefly summarize the main features of motor protection. Although the range of protection available is quite varied and not all relays are installed on all motors, we can divide them into distinct categories. The first is a stator fault, that is, a ground fault or short circuit due to insulation failure. Protection for this is provided by instantaneous overcurrent relays, 50, instantaneous ground relays, 50G, inverse time ground relays, 51N, and differential protection, 87. Overload protection is provided by thermal overcurrent relays, 49, in combination with time overcurrent relays, 51. Locked rotor protection may be provided by the time overcurrent relay or an impedance relay, 21, or an acceleration relay, 18. Protection against unbalance is afforded by a negative sequence over voltage relay, 47, connected on the bus, or a current balance relay, 46, connected in the supply leads to the motor. Protection against undervoltage or loss of voltage is provided by an undervoltage relay, 27, connected to the bus. Where a contactor is used, it will drop out automatically when the voltage falls. With synchronous motors, additional relays are usually provided, such as the loss of excitation relay, 40, the over-excitation relay, 76, rotor winding temperature relay, 49, underpower relay 37, the reverse power relay 32, and the loss of synchronism or out-of-step relay 78. In order to get a practical feel for this subject, you should make a detailed inspection of the auxiliary equipment installed in some of your company's power stations. It will also prove interesting for you to visit some large industrial customers on your system. Please switch off the tape now and thoroughly review this material in your workbook.